Ah. Things that we're doing in lab right now, we're designing and planning and carrying out experiments. So you guys are in the beginning phases of those designs of what you're going to be doing in lab. Interpreting graphs and figures, writing a lab report. These are all things that are either happening in lab or in the very near future will be happening on Monday in lecture when we talk about the methods and results section. So on Monday, you need to bring a one-page summary of the methods and results section of the Hendry et al. Paper. So we're slowly working you through this paper so that when the final summary is due, whatever day that is, October 11th, it doesn't jump out at you and it's like, oh no, I have to read this paper, I have to understand this paper, and I have to write a summary of this paper. So we're kind of staging you through this so that as you prepare for October 11th, it's not too overwhelming. So today in class, we're also going to talk some about how to interpret graphs and figures. At the beginning of every case study, we will go through a little day about statistics, where we tell you about the statistics that are going to be employed in the paper that you're reading. How many of you have been reading the methods and results section of Hendry et al. In preparation for Monday's assignment? Okay. Those of you who have, do you understand what they did statistically? No. Okay, that's why we're doing this today. So that's the purpose of today, is once again to equip you to summarize the methods and results, once again getting you on the way to this thing that's coming up on October 11th. So unfortunately, we pick papers not because they have stuff that's easy in them necessarily. We pick papers because they're a good example of a particular concept. And this happens to be one of those papers where the paper is good, but the methods that they use are way more advanced than you guys need to be concerned with the details of. But what you do need to know is you need to know conceptually what's going on. Hopefully, if you did not watch that video on principal component analysis, you should go back and do that. If you did, hopefully what I'm about to do with you will make a little more sense. So they employ a method called principal component analysis. Principal component analysis is what is the thing that resulted in this thing on the x-axis, this thing called PC1. PC just stands for principal component. This is principal component 1, and we'll see what that is like here in a few minutes. But it's crucial that you understand these figures in order to understand what Hendry et al. Are talking about. And the x-axis here is an overall measure of size of a finch's beak. Now, size is complicated because is the beak long? Is the beak deep? Is the beak wide? Those are all aspects of size. And shape, yes. So you can have short pointy beaks, you can have long pointy beaks, you can have short stout beaks, you can have long stout beaks. So size and shape are both aspects of a bird's beak. And the tricky thing is in both of those cases, those things require you to look at more than one variable. You could just look at length, but that wouldn't tell you everything there is to know about the size of the finch's beak. So they use principal component analysis to get at an overall measure of size. So what principal component analysis does is it deals with situations where you have multiple variables that might or might not be correlated with one another. When this happens, you can't treat those variables as independent variables because the length of the beak of a bird might be correlated with the depth of it and the width of it. So that's a unit that is it's an organized whole, it's an integrated whole, and so you can't just look at the individual pieces of it and treat all of that as independent data. And so in some cases, the variables that you're looking at are actually different aspects of the thing that you're really interested in. So beak length is related to size, beak depth is related to size, beak width is related to size, but none of those by themselves is size. All of them together are size. And so what principal component analysis does is it allows us to take these variables that are not independent of one another and combine them together into a common variable that represents the thing that you're actually interested in measuring. And so these are some of the finches that they mentioned. This is Geospiza fortis. It's a medium-sized beak finch. This is Magna rostra. It is the large beak finch. And so this was unclear to many of you when you wrote your introductions. They're not looking at 3 different species of finch. They're looking at one species of finch. It's confusing in the introduction because they mention 3 species of finch, but don't get confused by that and think that they're actually working on all 3. They're just working on Geospiza fortis. So you can measure the length of the beak, and you can measure the depth of the beak, and you shouldn't be surprised that you find that those things are correlated. And these are actually finch beak data from the Galapagos. If you have a longer beak, you're probably a bigger bird, and so you also have a deeper beak as well. In a similar way, if you have a longer beak, you probably have a wider beak also, once again, because you're just simply a bigger bird. So these things are correlated with one another, but they're also probably correlated with the size of the individual as well. And if you look at the width of the beak, you're going to find that it is also correlated with the depth of the beak. So these things are not independent of one another. As one measure of the beak gets bigger, all of the other measures of the beak get bigger. So you can't treat them as independent sources of data. So you can think of them, though, as a 3-dimensional data set, such that as depth goes up, width goes up, and length goes up. So this is a cloud of data points that goes from this far left near corner to the far right far corner at the back of this cube. As you go across depth, width increases, but also length increases in the z-axis going into the board here. So what principal component analysis does is it basically asks the question, is there another axis, not depth, not length, not width, over which the data vary the most? So I struggled for a number of years with how to present this data to students in a way that would be meaningful to them. And I finally just broke down and made a model. This is a model of beak finch data. Goes from this corner to this corner. You might be increasing in beak depth. Going from this corner to this corner, you're increasing in beak width. And as you go from this corner on the blue axis to the back of the thing, you're increasing in beak length. Okay? So it's a 3-dimensional data set. It's just fishing line and fishing weights that I've painted orange so that you can see them up against my principal component analysis shirt. Whenever I do principal component analysis, I always wear a black shirt so that you can actually see the data points. So when you look at this thing, as you're turning this thing around, you see that there's more variation going from this corner up here to this back corner back here. So if you turn this frame this way, you see that these data points extend over the greatest variation by looking at it this way, not this way. And it's because all 3 of these variables are changing in concert with one another. They're correlated with one another. So what principal component analysis literally does is it basically asks the question, where is the most variation? Well, you see the most variation when you take this frame and turn it this way so that this corner is far left to you, this corner is far right to you. But you'll notice that it's still going from a low value here to a high value here. What you then do is you basically say, well, this is the new x-axis. And so it turns it so that this is the new x-axis. So you see that there's a horizontal orange line here that I've made with fly fishing lead. And you can see that that line goes from this corner over here to this corner over here. And that encompasses the greatest amount of variation. So principal component analysis, the first thing that it does is it asks of your data set, where does most of the variation lie? Is it along the red axis? Is it along the blue axis? Or is it along the green axis? Or does it lie along an axis that isn't any of those? Then it says, okay, now I've found the greatest variation. I'm going to turn that so that that then becomes the new x-axis. Oh yeah, I forgot. Don't take notes right now. Just listen to me, watch me. We're going to go back through this, and you can take notes later. I forgot that I usually go through this twice. I want you to be paying attention to me rather than taking notes. We'll go back through it again, and you can stop and take notes. So now we have this new x-axis, but watch what happens to the spread of the data, the variation in the data, as I spin this box around the x-axis. What's happening to the variation? It does change. Tell me when you see the most variation. Oh, right there. You see less variation right here, right? Less variation right here. Less variation right here. More variation right here, right? So that's the thing that principal component analysis does next. Once it's taken this, it said, where's the most variation? The most variation is here. Make that the x-axis, then it spins the data set on that x-axis until it has it arranged such that there is a second axis of variation that represents the most remaining variation that is left over. That then becomes a y-axis, and you can see that there's another little orange thread going through the data set. So we now have a new x-axis, and we have a new y-axis. And these two axes quantify the most variation going from this corner to this corner, and then the next most variation, which is kind of going from sort of down here somewhere to sort of up here. So principal component analysis will make as many principal component axes as you have variables for, but it's usually the first couple of axes that account for the most variation. We could draw an axis through this data set that went vertically here, but that would leave a lot of horizontal variation in the plane coming at you that's not explained by that axis. So we turn the data set such that that variation is explained along the y-axis here. So we've taken three axes, red, blue, and green. We've turned the data set in 3 dimensions so that there's a new x-axis and a new y-axis, and those two axes account for the most variation in this data set. That's what principal component analysis does. It does it using a lot of really complicated math. And if you ever go to graduate school and you need to know principal component analysis, you'll probably have to take a class to learn how to do it. But that doesn't matter. What matters is at the end of this, you have two axes, an x-axis and a y-axis. Before you did all this turning, are these points correlated with one another? They're not. As the red axis gets bigger, what happens to the green axis? It also gets bigger. What happens to the blue axis? It gets bigger. So these are correlated. one of the things that principal component analysis does is in the process of finding this variation, making that the x-axis, and then finding the other axis of variation, are these data points now correlated with one another, or does it just look like a random cloud? It looks random, doesn't it? So one of the things about these axes is they're independent of one another now. So we go from this three-dimensional conformation, we pull this corner back, we pull this back corner forward, and we twist it until it's a solid, flat x-axis. Then we spin that, looking at the variation as we spin it around that x-axis, and when we get to the maximum variation, we then say, okay, well, that's the conformation of it, and we put a y-axis through the middle of that data set. And what we get is we get principal components. And when you have principal component 1 and principal component 2, principal component 1 has the most variation in it. Principal component 2 has the next most variation in it. But these two principal components are not correlated with one another any longer. And in this case, what becomes principal component 1 is actually size. How long is the beak? How tall is the beak? How wide is the beak? Those are the things that become principal component 1 in this case. Principal component 2 is actually a shape thing that they don't really talk about. But those three things, length, depth, and width, also affect this other variable, shape. But most of the variation in finches is size variation. Less of the variation is shape variation. Go back to these photos. This is a bigger beak than this beak, but imagine if you just blew this guy up, the shape of this beak would probably be pretty similar to the shape of this beak because they're all proportional to one another. So what's really happening here is this beak is just a blown up version of this beak. Size variation is more variable than shape variation for these reasons. You have the PowerPoint, you have access to the PowerPoint, open it up in PowerPoint, just grab the corner of this guy and blow him up. And you'll see that this guy, not only is his beak smaller, but his overall head is smaller. Blow this guy up, the only difference between these two things really is size. Larger bird, larger head, larger beak, similar shape. So if you have a principal component analysis and you create these new axes, hopefully they make sense. And you can call one of them principal component analysis 1 is size, principal component analysis 2 is shape. It doesn't always work out that cleanly. If you've ever done principal component analysis for real, sometimes you get your principal component 1 and you're like, what the hell is that? It doesn't really make sense in terms of you thinking about whatever project it is that you're working on. But a lot of times, one of the advantages of principal component analysis is that the new axes that you have will actually make intuitive sense to you as you're thinking about your project. I wrote a paper a number of years ago about landslides and patterns of succession on landslides. We used principal component analysis, and luckily, those things more or less made intuitive sense as to kind of how landslides recover after a landslide occurs, recover in terms of the plants that come back on the landslide afterwards. All right, take notes now. Three-dimensional data set. These data are all correlated. You have size, length, width, depth, whatever they are. All principal component analysis does is it's taking this three-dimensional box and spinning it in space. First step, find the most variation. Second step, turn that variation so that it's a new x-axis. Is that the second step?
Find the variation, then go to the x-axis.
Find the variation, turn that into an x-axis. Third step, spin it around that x-axis until you find the next greatest amount of variation. Turn that into a new y-axis.
The reason you spin it is because the new y-axis has to be perpendicular to the x-axis as x and y is overgrown.
Yep. Now, all of these data points will have a new value that is a numerical combination of the red, the blue, and the green axis, telling you where this thing is in now two-dimensional space. But it corresponds to the new axes. The new axes are linear combinations of the old axes. So all the original data is still present in the data set. You've just taken this three-dimensional thing and you've turned it into a two-dimensional thing. So now you have two new principal components. They're not correlated with one another, and you have fewer variables that you have to worry about. And the fact that they're not correlated with one another basically tells you that principal component 1 is telling you something different about your data set than principal component 2 is. In this case, what they're telling you is about, for principal component 1, its size. Principal component 2 turns out to be shape. In this paper, do they talk about shape at all? No, they don't. They talk about size. They could talk about shape, but my guess is it was probably harder to interpret than size was.
You could go to the figures, and where it says PC1, you could write that.
Size. Yep, exactly. And if you're on the far left-hand side of the graph, that's small-beaked finches. If you're on the right-hand side of that graph, that's large-beaked finches. So that's all they're doing, is they're taking these three things that have aspects of size in them individually, and they're combining that into this principal component that instead of being three components of size, it's actually size. If you want to explore this further, the data set that are in these slides is also on the Moodle site. There's a data set called Finch Beaks, and this little bit of code basically creates a three-dimensional plot, and the three-dimensional plot is fully movable around. So you can actually do the thing that I was doing with this physical frame. You can do it with a three-dimensional frame within R. I quite frankly find the physical frame to be a little more intuitive, but it has beak length, beak depth, beak width all here, and you can actually scroll over the points and see what the actual values are. I also did the principal component analysis on these data and got principal component 1 and 2, I got principal component 1 and 3, and I got principal component 2 and 3. And you can see in all of these plots, these data are independent of one another. They're not correlated with one another any longer. And I'm not actually sure what principal component 3 would be interpreted as, but it explains practically none of the variation that's left over. So once again, principal component 1 explains most of the variation. Principal component 2 explains the second most, such that when you get to principal component 3, there's not a lot of variation in the data that is left to be explained. Yes, ma'am?
Why is it important that the size and the shape aren't correlated with one another?
Because when you are, especially when you're doing statistics, one of the assumptions of most statistical tests is that the data that you have are independent of one another. And so if you have 80 finches, the length of their beak, the depth of their beak, and the width of their beak, those are all actually telling you similar information about that finch. They're not telling you independent information about that finch. Those are all related to one another. Generally, if you have a longer beak, you also have a deeper beak and a wider beak. And so those things don't exist independent of one another, and you would like your data to be independent of one another. So how many of you guys have ever been involved in a sport? Okay. Any of you guys run track or cross country? Okay, fewer of you. Play football? Oh yeah, our football team's gone today. Is the foot? Huh?
I'm there.
Oh, you're here.
They left me.
They left you. Oh, that. Oh yeah, you can't play. I ran cross country in high school, and I ran track in high school, and I also, you will find this shocking, I also played football in high school. No, it's ridiculous. So in eighth grade, I was the biggest kid in eighth grade. In ninth grade, I was the smallest kid in ninth grade. So I went from playing offensive line in eighth grade to being a wide receiver in ninth grade because I basically was the height that I am now in ninth grade. But I was actually pretty good at cross country. I suck at sprinting because I have the build of a distance runner. I do not have the build of a sprinter. So, for example, if we looked at one's height and one's weight and one's speed and one's endurance, we would actually find that those things are all correlated with one another. Your ability to run fast, your ability to run long distances is influenced by how tall and how heavy you are. So to think of sprint speed as being independent of these other aspects of your morphology is to simplify sprint speed and not recognize that these other factors are influencing it. And so what you might want to do to get an idea of performance is to measure one's height, one's weight, specifically measure one's leg length relative to their body length and their weight, and correlate that with speed. And you're going to find that there's a correlation, but all of those together might go into something called performance. And what you might find is that one distribution, if you did a principal component analysis of that, what you might find is that one end of the distribution you have sprinters, at the other end of the distribution you have distance runners. And speed doesn't necessarily tell that whole story. Endurance doesn't necessarily tell that whole story. Height doesn't tell that whole story. Weight doesn't tell that whole story. But all four of them then allow you to divide your population into people who are better at sprinting versus people who are better at distance. Does that make sense? Okay. Sometimes it's just a matter of finding the appropriate example. All right. You're never going to have to run a principal component analysis. What we've talked to you about today is the level of understanding that you need to understand it. If you have to use a sports analogy to do that, by all means, use a sports analogy to do that. But that's what this is doing. It's taking three variables that are not necessarily independent of one another, combining them into a new variable that represents this aggregate variable size. Okay? So that's how they get these figures where, and unfortunately they do not label their axes in these figures, where size, principal component 1, is on the x-axis. So the next thing that you have to think about as you're reading these papers is this, reading this paper is this idea of bimodality. So bimodality, we'll talk about this more next week, but normally we oftentimes think of populations having a normal curve. We lined you guys up the other day in class from tall people to short people. And if we had a big enough population, we would see that that's a normal population. There are a few really tall individuals, there are a few really short individuals, but most individuals are kind of clustered around the average of the population. But not all distributions are like this. You can have distributions that are bimodal instead of unimodal, where you have a lot of short people, a lot of tall people, and very few average or intermediate people. This is a bimodal distribution. This is a unimodal distribution. Now, Which of these are bimodal? C. How many of you agree? C is bimodal. Okay, virtually all of you. Which one of these is unimodal? You guys are making this too easy. What are those other two?
A is also bimodal.
Okay, you might want to say, okay, well, A looks a lot more like C than perhaps it looks like D. What about B? You might say it's trimodal. It has two little side humps, two little high modes, and a big central mode. But you might also argue that this distribution is more like this distribution. So the question is, at what point do you shift from saying this is no longer unimodal and is moving more towards bimodal or trimodal? At what point is this deviating enough from unimodal that you can say that it's truly bimodal? That's what they're trying to do in this paper, because their hypothesis is that these birds have been diverging morphologically for decades, hundreds of years, maybe thousands of years, millions of years prior to humans coming here. And what is happening, they're arguing, is that they're taking a bimodal distribution of finch beaks where you have large finch beak, you have Geospizophorus with large beaks, Geospizophorus with small beaks, and something is changing as a result of human activity that is converting the beak distribution from this distribution into this distribution. But as you shift from this distribution to this distribution, there could be a lot of variation in what that distribution looks like as you move from a bimodal distribution to a unimodal distribution. So they need ways of kind of objectively saying, this is unimodal versus this is bimodal. Or this is more likely to have come from a bimodal distribution than a unimodal, or it's more likely to have come from a unimodal distribution rather than a bimodal distribution. So that's what these figures are all about, is them trying to figure out how to parse A and B. Is it unimodal or is it bimodal? So, let me make this bigger so you can maybe see it a little better. This is a terrible graph for a number of reasons. One reason is that they don't explicitly label in the figure what the x-axis and what the y-axis is. So let's do that first on these figures. You can get what the axes are from the figure, but you have to read the legend. You have to read the caption. So the x-axis is principal component 1, which is also what? It is size. Size from large-beaked finches on the right to small beaks on the left. The y-axis is the cumulative probability distribution. Now, what the heck is that about? As you move, so let's just say that this is a bimodal distribution. Well, let's start with the unimodal distribution. We have small beak finches and large beak finches. As we move from small to large, if we're taking hunks out of this distribution of data, at the beginning, are we accumulating data very quickly? We're not, are we? But as we get further into the distribution, do we start to pick up the rate at which we're accumulating data? We do. As we get into the bulk of this, all of a sudden we're picking up lots of data with each new increment until we get past that hump. And then what starts to happen in terms of the rate of picking up new data? It declines again as we get out into this tail. This cumulative distribution is just a graph of that. It's plotted on a logarithmic scale such that a normal curve looks like this. At the beginning, you're picking up relatively small amounts. In the middle of the distribution, you're picking up larger amounts of data as you move across this distribution. But it appears as a straight line because you've graphed this on a logarithm rather than graphing it with normal data, with a scale. So it's the log of the data. And so this is what you would expect if the data were normal or unimodal. Pick up a little bit of data at the beginning of the distribution, more data in the middle of the distribution, and less data at the end of the distribution in terms of the accumulating data. If you didn't have this as a log distribution, it would look like this. Picking up a little bit of data among the small finches, picking up more data at a faster rate in the middle, and then that tapers off at the end. But if you take this curve and log transform the data, it will turn it into a line. Okay? But what happens in a bimodal situation? At the beginning, what's happening? You're picking up a little bit of data, but then there comes a point where you start to pick up more data because you're in this first mode. But then what happens as you get to that valley? You're picking up less and less, but then you get past that valley, and what happens? You start to pick up more until you get to the end when you then start picking up less. Had I thought about this, I would have drawn this differently. But now I will just recreate this over here. Here in the unimodal case where you're picking up relatively little data, in the bimodal case you're picking up a lot of data. Here in the bulk of the distribution where you're picking up a lot of data in the unimodal case, you're picking up very little data in the bimodal case, and then when it starts tapering off in the unimodal case, you're back to picking up a lot of data in the bimodal case. So if this is what you expect in the unimodal case, in the bimodal case, what you should see is that at the beginning you pick up less because there's just less data down here because it's actually split into these two modes. But then early on, you start picking up more data than you would expect. So that by the time you get to the middle of the range of size values, you're way above the expected line. But then you go through this valley and it slows down again until both curves kind of converge on one another at the end. So a bimodal distribution, when you graph it this way, looks like this kind of S curve, whereas the expected unimodal curve looks like a straight line. And so when you look at these figures, you're asking yourself, whoop, I've drawn it slightly wrong. It starts out below, then goes above, then comes back below again. Yeah, because you're at this end over here. So when you look at these figures, what they're basically asking is, do the data kind of conform to the straight line, which represents a unimodal distribution, or do the data, as you accumulate them, do they deviate from that line, such that instead of a straight line, you have this curved line? Gathering a lot of data, then slowing down, then gathering more, versus just gathering data at a constant rate across the range of sizes. Gathering more data, then less data, then more data, versus, once again, gathering data at a constant rate throughout this figure. So once again, the way you think about these data are by thinking about how much data do you accumulate as you move through this, cumulatively, as you move through this. Do you gather a lot, then it slacks off, then you gather a lot, or do you gather a little, and then a lot, and then a little? And that's all these figures are showing you. Now they do some statistical tests to try and get a more objective view on this, which you don't really have to worry about those at all. But the results of their tests is that it allows them to say, well, these data that we observe, so the line is what you would expect from a unimodal distribution. The data points are what they actually observe in the birds. In this case, at Academy Bay in 1964. And then they do these tests, they do these graphs, and they try to determine whether or not those bird data are more likely to have come from a distribution with 2 peaks versus a distribution with 1 peak. And so when they have more confidence that it came from 2, they put 2. In some cases, they conclude, mainly because of really small sample sizes here, that it was just as likely to have come from a bimodal distribution versus a unimodal distribution. In other cases, they conclude that it's way more likely that it came from a unimodal distribution rather than a bimodal distribution. One way to think about this is you have these two plots here. These are both unimodal. Well, yeah, just as likely to be 2 as 1, slightly more likely to be 2 than 1. But this is definitely bimodal. Once again, the heavy accumulation early, then slacking off, then accumulation late. So this figure is a figure that, once again, you can download these and view them in like a PDF reader or something like that, or in Preview. But this is another one of those situations where it's most useful for you to open it in PowerPoint and run the animation. So imagine that you're starting out with this first bird in the distribution, and you're going to go all the way to the last bird in the distribution. Well, as you move through this first peak, you accumulate a big chunk of the data because you're moving through that first peak. Then you go into this valley, and you're accumulating less, so you come back to kind of where the line is expected. As you move through that valley, you then dip below that because you're still in the valley, but then you hit that other peak, and it returns you back to the line. These data points are this distribution graphed against what you would expect if you had that data coming from a unimodal distribution. If it came from a unimodal distribution, you would expect it to lie all along the line. But it's not lying along the line, it's deviating from the line. And that's how you know that it's a bimodal distribution. Does that make sense?
Does that make sense? Sometimes people spend a lot of time describing the method and how they did this in their literature summary, and this is where you can be concise. The whole reason they did this is to detect whether it's unimodal or bimodal. And if you imagine just putting a unimodal distribution here, kind of like focusing on the board there, and ask you to make a decision, it's actually much easier for the human eye to detect deviations from a straight line than to compare 2 curves. So that's why they're doing this. You guys don't have to worry about the AIC model selection and all that stuff. You could say that in a phrase of notes.
Yeah, so let me go and get this. This is figure 3. These are the distributions, and you'll see that Academy Bay 1964, Academy Bay 1968. These corresponds to these figures, Academy Bay 1964, Academy Bay 1968. You could yourself cut these figures out of the paper, stack them on top of one another, and do that same animation that I just did, and you would see that you get this bimodality. You could also take Academy Bay, Barrero Bay, or let's see. Yeah, you could take Barrero Bay and look at Barrero Bay here and stack those on top of one another and do that same exercise like I was doing on the board. It's a little bit of a pain in the butt, but if you really wanted to make sure that you understood why they're saying Barrero Bay is a unimodal rather than bimodal, that's the way to do it. And take yourself through this process of how does data accumulate. Data accumulates a little bit at the beginning, a lot in the middle, and then it tapers off again at the end. Any questions? Yeah. Hmm? Oh, yeah, yeah. Yeah, you don't have to ask. Well, you send us an email. We're good. Yeah.
So in our summary, should we just assume the reader knows what like principal component analysis is and that?
Yeah, we don't want you to spend time explaining how principal component analysis works. What you need to know and what you need to communicate to us is that they use that technique in order to get at size that is this multivariate thing, but they're trying to get at size in a univariate sense. Take these three variables that relate to size and compress it into one variable that is now size. Same thing with this. All you need to do is say, that they were attempting to use methods that would allow them to distinguish between when distributions were unimodal versus bimodal, when there was a single central peak versus two peaks spread out. Because that's ultimately what they're talking about, is divergence of phenotype versus convergence of phenotype. And trust me, if you are trying to explain that in your own words, we're going to be able to figure out whether you're really understanding that or not, because you're relying on your own words rather than the words of Hendry et al. And that's the tricky thing. How do we break this down in ways that allow you to communicate about it effectively while not going into so much detail that it just becomes overwhelming to you? So that's the balance that we're trying to strike, which is why we do stuff like build models out of PVC pipe and fishing weights. Other questions? Hopefully this equips you to better handle the methods in the results section. That, once again, is the whole point of doing this. If we didn't have you read this paper, we would never talk to you about principal component analysis and how you go about testing for bimodality. There would be no point in it. Okay? All right, you have comments about the papers?
I have, yeah, so your Hendry versus summary, you have feedback for you already saw. When you're working on this, make sure to go to the literature summary link at the top of Moodle and
Yes.
read the formatting instructions. It's important for you guys to be able to follow formatting instructions as part of being a scientist. In this case, for example, the references should be in the same format as the journal that the paper came from. And going up here, it also makes it a lot easier for us to grade these and give you good feedback, and a lot easier for us to handle the files. If you name the files properly, put your name on the top so you can print out and annotate them, and then put our feedback in your double space work. So you should all have access to Microsoft Word. It's a great program to be familiar with if you don't use it all the time, because it's something that's, no matter what query you end up in, you'll probably have to write in Word at some point. So it's good to get comfortable with that now when you have free access to Microsoft 365.
So here in Moodle, at the very top, under what is called General, there is a whole folder full of stuff that is intended to help you write your literature summaries. And we'll look at what's in that folder in a minute. I also went to the trouble of taking the Lyon et al. Paper, which is the Coote paper, which you have now all read, and I have written what I think would be a exemplary literature summary of that paper. So if you want to see, well, how much depth do I need to go into in the methods? How am I supposed to be structuring this? How much of the paper needs to be focused on summary versus critical thought, and what does that critical thought actually look like? You can go there and say, okay, well, this is what Dr. Klawinski would have turned in, having a PhD and 20 years of experience reading this paper over and over again. This is what he would have written. That serves as a good template for you. Ruth Bader Ginsburg was well known for being a very clear and concise writer, and there was a story about her on NPR, I think, a number of years ago, looking at her clerks and asking her clerks what they learned from clerking with her about how to go about writing. It's got some useful advice in there for you. When you look at this folder here, Help and Guidance, you will see that it has the assignment. So the assignment that is due on October 11th is right there. And this is what it is. Tells you it's a 2-page summary, page and a half of it should be in summary, a half a page should be in critical thought. It then goes on to talk about what we mean when we talk about critical thought. I was just interacting with our juniors and our seniors who are going to be presenting literature, doing literature presentations, and it was clear from talking to a couple of them that they still think that expressing critical thought towards something is finding things wrong with it. That is not what critical thought is. Critical thought is thinking about the thing that you've read and basically synthesizing that information. And for us, better forms of critical thought are not trying to find things that are wrong with the paper, but thinking about what the next steps would be if you were going to continue to ask questions about this system. So it gives you some examples of that. This is also largely found in the syllabus, in the section in the syllabus dealing with literature summaries. Down at the bottom, these are the formatting instructions, so they're there. The one thing I will tell you is we'll have a Moodle assignment on there for the October 11th one, so it'll be a Turnitin assignment. That is mainly because when you turn it in, when you turn it into Moodle, it will run a plagiarism check on that. We want you to hand them in to us on hard copy because it's easier for us to grade those. You'll see on the things we write stuff all over the page when we read these things. So you don't have to worry about, these are instructions from last year. You don't have to worry about naming your files and things like this in this way because we're not ever going to download those. When we were here for pandemic, we didn't ever see our students in person during class, so we had them submit them.
Still, it's a good habit to be in, especially for future classes, or if you're going to be out of town for athletics or something.
Yeah, if you are out of town, then you can certainly turn it in that way and say, hey, I'm out of town, but it's on Moodle, and we can go and download that. What we don't want to be doing is downloading 30 files and saving them on our computer and dealing with them digitally. Yeah? Yes, the way that it is set up, you can submit it multiple times because we want you to find plagiarism. Some of you are already having difficulties with that in the first assignment. Especially substitution plagiarism, which is one of the most common forms of plagiarism. I made notes on that. I'm sure Dr. Judd did as well. So if you do see a note on there, this is a practice homework. We had not talked to you at all about plagiarism prior to this, so it's like no big deal. But stuff that you write later, now that you've been through whatever Dr. Judd prepared for you, now you're aware of different forms of plagiarism, how to write in ways that avoid plagiarism, et cetera, et cetera. So we will be thinking about that as we move forward. Our goal is to never hold you accountable to something until we've actually taught you about it. Which leads me to, does anybody have any question for Dr. Judd about what he prepared for you for plagiarism?
I want to make sure we get these back to you, so I'd like to take at least a moment, only on Monday, to talk about those examples we worked on. That way more people will be present and it's all happening today. And as I said, if you're working on these drafts, refer back to those slides or reflect in the video if you're concerned with plagiarism. If you're still concerned after you return back, come see us in your drafting phase. We're here to help you avoid that. We want you to learn the skill of responsible writing.
Did you all buy the writing guide that is in the syllabus? Do you have the writing guide in your possession? Okay. If you don't yet, buy it. Chapter 6 in your writing guide is entitled Revising Your Paper. And it's designed to help people revise something that they've written But what it's really good for is to read before you sit down to write, because it will point you towards common mistakes that students make. And it's better to avoid mistakes in writing than to make them and then have to go back and fix them. So read that chapter. One of the first things that is in that chapter is avoiding running jumps. You should know what a running jump is because a bunch of you had running jumps in your writing. So you need to ferret those things out. Yeah. Yes, 2 pages, no longer. And 2 pages no shorter either. The rationale behind why we have a page limit and the reason that we have formatting instructions for this assignment is that we want you to force your summary into a page and a half because we want you to get in the habit of paying attention to what's truly important versus what is not so important. So as we took you through that exercise of how to read a scientific paper with the Coop paper, we want you to be honing in on the things that are truly crucial to understanding the paper rather than concentrating on things that are less crucial. So we have that assignment written this way because we want you to have to choose what you include and what you leave out. When you get to genetics, you will read papers. You'll have 10 sentences. Period. What? Yeah, sure. 10 sentences. So once again, that isn't arbitrary. Dr. Reynolds does that because she wants the students to really be honing in on what's truly important and also get good at summarizing things. Because when you go to write an actual real paper, you might summarize an entire paper in a single sentence. So this process of taking a big thing, reducing it to a page and a half, taking a big thing, reducing it to 10 sentences, taking this big thing and reducing it to a summary sentence is a process that you have to practice in order to learn how to do that. This is just the first step on that. So yeah, that's the reason. Once again, the page limit isn't arbitrary. It's done for a reason.
So let's say for so you have delete information from one of your pages, right? And you want us to add more information so it's a full page.
So shoot for 2 pages. If it's a page and a half, chances are when we read the introduction, we're going to find that you didn't talk about things that you probably should have. We'll find in the methods that you probably should have talked about things that you didn't because it's so short. And I actually made a couple of comments on a couple of people's papers that were similar to that. Your summary wasn't a full page, and because it wasn't a full page, you missed some key elements that you probably should have included. Same thing with people who had more than a page. It's like, well, you had more than a page, you included everything, but you didn't write it very efficiently such that it didn't fit into the page. Now keep in mind, we've given you an assignment where we asked for a page summarizing the introduction, a page summarizing the methods and materials. Well, you can't just take those 2 things and then plunk them into your final version because that's 2 pages and you have no room for critical thought. So the other reason that we're doing these introductory drafts is so that you can get feedback on them so that when you do write the final, you can say, I was too wordy here. How can I clean up the writing and make it shorter, make it more concise, make every sentence mean exactly what I want it to mean. Does that make sense? No, he's going to go through that at the beginning of class on Monday, I think he said. Yeah. Yeah, it's just we're out of order now because life happened. Questions? All right, enjoy your weekend. Let us know if you have any questions about the paper.
Did you get my email about
Yes, I did.
Okay.
I just haven't responded to those yet. I'm still processing through those. Yep.
Okay. I love your watch. I didn't mean to touch you.
Oh yeah. My digital watch, which I normally wear, has started fritzing out on me, so I'm wearing my nice watch more than I usually do. Bring your mask next time.